And this morning, I'm delighted to welcome Dr. Paul Collegia here, who heads up the Cambridge Zettascale lab. So they're our local hosts. So first of all, thank you very much for you and your team for hosting us all. It's been very much appreciated. And their lab is doing some really, really interesting stuff, lots of which is using SYCL and related things. So hopefully Paul's going to tell us all about that today. So thank you, Paul. Over to you.
Problem. I'm happy to be able to host you here in Cambridge. I hope you're enjoying sunny Cambridge. So you came on the right 2 days, which is good. And Simon's given me the opportunity to speak about what we do here. So really, what do we do? The title says it all really. We provide advanced computing services. So we're an HPC service provider. We also have quite a large technology innovation activity. And we do this obviously to drive research discovery. We do a lot of work, specifically in clinical medicine, on improving health outcomes. And we try to do quite a lot of industrial engagement and economic development. Obviously, that's really meant for government sponsors. It all has to be about the economy if you want money from government. And I'm director of the Research Computing Service here. I'm also director of an industrially funded lab, which we call the Zettascale lab. Okay, it's a little bit of an oversell, but you know, marketing people do get carried away with themselves. And I'm technical director of a UK square kilometre array project to build a large distributed science regional data centre infrastructure for the SKA, which is a large radio telescope, but I can talk about it later. It's not working. Okay, that's right. Yeah, thanks a lot. So just a little bit about the university. Since you're here, you might as well know the place you are sitting in. So there are over 70 academic faculties and departments across the university, 140 different research institutes with specific areas of research. So that's a very active research and development institution. We have around 1,500 tenured academics. I am not tenured academic. 3,500 contract research staff, 4,000 PhD students. That's around kind of 9,000 research active employees. We turn over around, these are a little bit out of date, we turn over around 1.5 million. We spend just over, sorry, 1.5 billion. We spend just over 1.5 billion. So the university is running on a deficit at the moment, as most universities probably are. And of that 1.5 billion, around 800 million is research economy. So that's quite a large research economy. We spend 800 million on research every year. Actually, more interesting than Cambridge is a tech cluster around Cambridge. So within an 8-mile radius of the university, you've got, again, these are old, so just bump the numbers up a bit. Around 60,000, I think, employees, 1,500-ish companies, totaling over £13 billion. That's why you can't buy a house in Cambridge. It's just impossible, as Chris knows. It's not buy a house. So, you know, house properties here are fueled by this mini boom. Yeah, and we work with a lot of these companies. There's a really tight interaction between the university and this tech cluster. And this paper just came out last week. It's quite interesting. Apparently they can back these numbers up, which I find interesting. Apparently the university adds around 30 billion a year to the UK economy, if you can believe those numbers. Apparently it does. Every pound spent here adds X pounds to the UK economy. So give us more money, I think is the message. So it's a very obviously structured document, but I think that's what they're trying to say. But it's actually quite an interesting read in terms of how money spent in a university percolates out through the rest of the UK. So why do we do HPC? Obviously, you know, most HPC guys kind of are scale dominated in their thinking. So we all think about the big science. So we're involved in big science projects. This is the square kilometre array that I spoke about. It's a very large radio astronomy project. It's one of the next big science projects akin to CERN. This $1 billion budget. It will run for 50 years. We've been planning it and designing it, I think, for 15 years, 20 years in the planning. It's just starting to be executed now. So telescopes, the 10 antennas are going down in the South African Karoo Desert and in Western Australia. You don't like to put radio telescopes near mobile phones. You put them in remote areas. it's a really large streaming I/O problem, and we're involved now in, once the telescopes generate the data, how do you distribute that data globally and process it in some kind of federated resource? That's a long-standing big science project we're involved in. We have another long-term collaboration with UK AEA. They're the people at Culham that are designing our nuclear fusion capability. How do they put it? Green, clean energy on the grid in the 2040s. That is their mission. But it's a really grand challenge problem in terms of the simulation couplings that's going on. It's plasma, materials, fluids at extreme temperatures. It's a really interesting science problem. And the only way they're going to get that working by the 2040s is to make a virtual engineering mock-up of the system. You can't build prototypes. You have to do it virtually. So that's a really big project that we're involved in. We're partnering with Simon's team in Bristol, working with them. And there's a lot of SYCL work getting their codes, GPU, obviously. So there's a lot of work. I'll talk about that a little bit later. We have another initiative run by Chris. That's why he's looking so tired. Trying to employ lots of climate modelers. We got some funding from Smith Futures that fund a lot of weather modeling across the world. And they wanted to form a kind of a single team to support that distributed weather modeling activity. That team sits here and Chris manages that. But, you know, as HPC guys, we're fixated on scale, and we often don't talk about the long tail. And this is really the important part of science, not the big science that sits down here. This is scale of use, and this is number of users. We get all excited and we talk about big science in talks because it's big and sexy and we all like that. But actually it's this stuff, the many, many small users where all the productivity comes from. And 80% of our workflow is small. 80% of my workflow can sit on under 8 nodes. That's where all the science is done. That's where all the publications come from. That's where all the value is generated, but we just don't talk about it because it's not sexy. And in terms of healthcare, we've got a whole load of healthcare projects. We did a lot of work in the COVID years. The one thing I'll talk about later is we run all our infrastructure within an OpenStack framework using modern OpenStack discovery, provisioning, and control tool chains. The main reason we moved to OpenStack was that we could create isolated tenancies. In those tenancies, we could put patient identifiable data so that my boss does not go to jail. That would not be a good thing. So that was the driver for our OpenStack work. We're now exploiting OpenStack in many ways, which I'll come on to. We held a lot of patient data during the COVID years, and a lot of the epidemiology models that were being spoken about on TV were calculated on our machine. We had another project that drove our OpenStack work was brain imaging, medical imaging. Again, there's many different types of medical imaging. Brain imaging is just one example. But now, as these machines get more high resolution, they produce more and more data. The normal processing tool change that the guys have in the hospital just couldn't cope with the new machines. This is in many fields: light sheet microscopy, genomics, medical imaging like this. They're all producing rapidly increasing data sets. The hospitals would have processed that data on in-house HPC systems in their broom cupboards. They just can't cope with that anymore, so they have to ship them out to remote services like us. That's just one example. And another medical project that we're heavily involved in is Genomics England. So Genomics England are a UK government-sponsored genome analysis activity that I think now collect routine DNA samples from every hospital in the country. It all goes into one big database. My team wrote that database technology. We spun that out into a company called Zettascale, and it basically can hold, millions, tens of millions of gene variant samples and assist clinicians in interpreting the outcomes of those genome studies. That's a really big activity that we're doing. So just come back down to earth. What does all this look like? What are we? So we provide HPC services both locally, people within the university, but also nationally with direct funding from the funding councils. And actually most of our business is national. That's split between national and local. 80% of our turnover and focus is on national HPC service. So most of my activity is focused outside of the university. Although a lot of those national users are actually users from Cambridge, but they're being funded through national consortia like DIRAC, IRIS, EPSA Tier 2. But many of those people getting funding through that route will actually sit in a university, but they're using national funds. And our growth rate there is quite high. We also undertake an increasing volume of development activities. I'll talk about those later in the deck. And currently today we have around £35 million worth of equipment in the data center. Once equipment in its fifth year, we throw it away. So we can't keep more than, if we keep equipment in there for more than 4 years, we run out of space. So there's a continued kind of equipment comes in one end and comes out the other. Otherwise, we just run out of space. And of course, the power, the computational output per watt and the computational output per rack U is so much bigger on the new equipment. There's no point in keeping the old equipment. Actually, we have an active program where we repackage that equipment, refactor it, and we send it to Africa and the collaborations we have in Africa. So the last system we have is, the oldest system we have at the moment is 1500 Skylake nodes. We're chopping that up into rack elements, shipping that out to South Africa, and then we use that as technology transfer. I have a slide about that later. So currently we have over 40 staff in the team. That should be rising to 55 over the next year if Chris can hire them. HR is a perennial thing, but we have headcount for 55, but staff is obviously a problem. So if any of you want a job, you're welcome to come and work here. It's a nice place. You don't even have to live in Cambridge. That's my sales pitch done. There you go. He's the man to talk to if any of you want to come and work at Cambridge and stay in your bedroom. That is now allowed, apparently. So we have 2 megawatts. This is actually a picture of our room, our hall. In that hall, there's 100 racks. Each one of those racks, the cooling is at the back door. So we have a water-cooled radiator that sits there in the back. So normal air cooled servers. Cold air goes in the front, hot air comes out the back, but the hot air doesn't escape the rack. It is cooled at the back door because there's a radiator filled with water there. So most of our servers are air cooled, but water at the back door. Although, of course, now if you're buying new servers, because the processes in those servers are getting hotter and hotter. It's the only way that the IT industry can keep the ball rolling and giving us more power per server. They have to just make the silicon bigger now and more hungry, and someone worked out that they could keep making it hotter if they put water directly on the chip. So now we're having water-cooled chips. Before water cooling chips, I think a chip was kind of limited. If you wanted a dense form factor, Simon, what, 200 watts, 240? You could go more if you had a big server and you had a huge heat sinks on, but if you wanted dense, the hottest was around 200 watts. Now with water cooling, we're up at, in x86 servers, we're up at 350 watts. Your GPUs are going to be up at 600-700 watts, and it's going to keep going up. Do you know what the limit is? It's over 1,000. Yeah, so you're going to be getting a kilowatt chip. That's crazy stuff. And the only way you can do that is if you put water on the chip. Yeah, so we've now got 10 racks of water-cooled chips. That is quite a steep learning curve. Water cooling on the chip is a little bit, plumbing becomes a thing. Yeah. If you saw that under my kitchen sink, you'd realize I'm not a plumber. But you can't do that shit in there because it's tricky. Water at the back door is tricky. But of course, your power density goes up, your energy efficiency goes up. So our PUE in here is really low. So our PUE is down at about 1.07. So what does that mean? It means we consume 7% of the power we put into the servers to cool it. Lots of traditional crack, hot oil, cold oil data centers will be up at around 1, 2 even. 2 is not uncommon. If you have no hot oil containment, if hot oil containment, you can probably get down to 1.7. So that'll be 70% of the power you put in. You have to add on again to cool it. This is 7%. Yeah, so it's really efficient. So we have around 11 petaflops of heterogeneous compute power via Impact. We're around 3,000 servers, a mix of x86, mostly Intel x86 and NVIDIA GPU. Some of the NVIDIA GPUs are AMD processors. We have 45 petabytes of storage. That's disk and tape. It's about 35 disk, 10 tape. And we are ISO 27001 compliant, which is quite onerous, but necessary if you want to hold medical data. That's taken a lot of effort. Getting that ISO compliance is a real heavy lift, but it does mean you can do a lot more work. So just some key characteristics. We've been running for 17 years, providing one of the largest facilities in the UK. We have a very cross-domain user stakeholdership, so we're not aimed at a particular domain. We cover all domains: life sciences, biology, astronomy, physics, social sciences. I think if I was to pick focus areas, it's probably medical and astronomy. Cambridge has a very active observational astronomy department that we work very closely with. And of course, the clinical school is very active, and we do a lot of work with those guys. Really, back when we started in 2006, we kind of pioneered the use of kind of large-scale commodity servers, because at that time in 2006, our national machines were still proprietary systems you'd buy from IBM or Hitachi. That was HPCX. Do you remember HPCX? You're old enough to remember HPCX. And so these were proprietary electronic systems. We came in with our machine Darwin at that time, 600 nodes. I think this was our highlight. We peaked early. So this was 600 nodes of Intel dual core. So if you remember at that time, Intel were not doing well against AMD for quite a while, and their Israeli team came up with this idea of let's put 2 different cores on a die, and this really revolutionized commodity computing. And Intel came back on top. This system was way outperforming what we expected to do. We got number 20 in the top 500 for just £2 million. Can you believe that? I mean, no way. I mean, that was crazy. And compared to the incumbent HPCX system, which was an IBM something, I can't remember what it was, we were 50x the performance per pound of a machine that was still in service life. And never again has a UK top-end supercomputer been anything but commodity. And that was the death now, really, at that period of those large proprietary machines. Yeah, they kind of died out because they couldn't compete with the commodity agenda. So we have a strong in-house technology team. So we do have a larger support team than many similar services. Why do we do that? We do that so we can undertake all the system design, implementation, system support, and user support ourselves, because we believe that provides us with the ability to do the best fit between science, need, and technology deployment. I think that's really the trick that people like me should be concerned at. I could build many HPC systems I'm interested in, but you as users might not have the same opinion. So we really have to have a close interaction between scientists, their needs, and how we can meet those needs with technology deployments. And if we're doing that ourselves, we can do that better than if I just buy a blue one from HPE or Cray or Dell. And provide strong value for money. One of the odd things about our service is we run as a self-sustaining cost center. There are all orthogonalities in here. Some things are bad because we have to run like a business within a public sector organization, which is a terrible thing. Because public sector organizations are far from agile. And if you're running a business, you need to be agile. And so there are many orthogonalities in here, which make me sad. But there are many more smiley faces because it means my money is my own. Therefore, I don't really have to talk to the university about what I want to do. It's not their money. I do what I like. Therefore, I'm still here. Otherwise, I would be gone. So I guess that's good. So there's smiley faces, more smiley faces and sad faces. And I just employ people to do things I don't like and pretend it doesn't exist. So that's all good. I would recommend that to all of you. If you don't like something, employ someone to do it for you. Blood pressure's down. Lots of smiley faces. So we have a strong focus on technology innovation. This is kind of like my hobby, really. And technology innovation by co-design. What do I mean by co-design? This is where we create this kind of virtuous circle of users, service providers like myself, and primary technology providers. And you put all those people in the mixing bowl, and you create a critical mass of requirements, of technology knowledge, of service provision knowledge, and you design by proof of concept cycles. Yeah. We've been doing that for a long time. It really works. Okay. So what does the service look like in the cartoon? So the bottom layer here is the hardware infrastructure, because I'm still a hardware monkey at the end of the day, really. I'm not really a software guy. I pretend to be a software guy, but I'm wires and plumbing. So a spectrum of technology, new on the right, old on the left. And as I said before, we just put stuff in this side, and then things fall off the end here. So these are now being decommissioned, cut up into racks and shipped to Africa as part of a technology exchange we have with the African Union, which is actually very interesting. Our newest equipment is a whole load of Intel Sapphire Rapids nodes. This is funded by UK AEA. So this is actually quite an interesting technology from Intel. Intel start to get their mojo back with this. It's actually quite an interesting platform. This is water cooled, 100 nodes now, currently 700 nodes of Ice Lake. Again, Intel, again, water cooled. Whole load of NVIDIA A100s. I think we have 400 A100s in 100 nodes. Previous generation Intel 600 Cascade Lakes. This is basically dead as well. And the Sky Lakes. We just continually push stuff in because we have a 2 meg limit. And when we get to 2 megs, something has to go. Yeah. All InfiniBand, apart from this is OPA. But once that's gone, everything will be InfiniBand. It's quite a complex network because as you add different generations of equipment to a network, you end up with different network technologies. That can be fun. At least if it's InfiniBand and they're reasonably close in generations, you don't need to route it. But if you have a real zoo in here, so this has to be managed really carefully, otherwise you get a real network in zoo, and then you have to have lots of routers, and then that doesn't end well because you get unpredictable failure modes when you have lots of routing going on. Yeah, and in the end, stuff locks up and you just have to shut down and start again. Yeah, so we got into quite a mess here actually in terms of too much of a technology spread in here because we weren't throwing stuff away quick enough. Yeah, so you have to throw stuff away quick enough to keep this manageable, and you have to plan it. Plan your deployments with this in mind, actually. Otherwise, you get a zoo. So all the hardware is deployed within a single OpenStack tenancy, and then we use that OpenStack tenancy to create a number of ways of accessing the resource. Okay, so with traditionally, most HPC centers are using cluster management technologies that are 30 years old from the DOE. Right? It's all 30-year-old boring stuff that people just keep doing. One big monolithic HPC service where the environment is designed to be the mean of your users' needs. So no one's really unhappy, but not many people are super happy, but they just have to suck it up. Yeah, this is the general Linux system admin, passive aggressive kind of, user support that I'm sure many of you are used to. Yeah, we have one of those. He's really good at that passive aggressive thing. And so you just suck it up, right? Because you don't want to push that guy too much, otherwise, it's not going well. But with OpenStack, you can change that whole thing and actually give your customers what they think they want, which is amazing, liberating experience. You should try it. So we do that. So still most of the service is still that bare metal slurmed shared service where you got to suck it up. Yeah. So it's still mostly that. It's still mostly that. But we can carve up the cluster. So we could, if your boss is important enough and moans at my boss enough, then we can give you your own private cluster. Yeah. Of course, it's always on, so you're always paying for it. So you better be able to use it. But you can have a customized bare metal infrastructure with your image and your own Slurm queue, and it's isolated from everyone else, and I can make it dynamic. I can grow it and shrink it. Yeah, so that's interesting. So that's starting to become popular. We can give you virtualized infrastructure or Kubernetes infrastructure. Again, this is becoming really popular, especially in astronomy. Well, astronomers now, anyone doing data science, just want a Jupyter notebook on Kubernetes. That's what they want. They don't want to sit in a Slurm queue. They don't know what that is. Yeah. So again, I think this is really how we're going to be deploying most of our infrastructure in the future. That's really taking off. We do have an infrastructure as a service activity where you can just come to us like we're Amazon, and you can say, I want XD servers, I want to administer them and run them. A lot of people in life sciences or groups that have data that they want to make available to community want to run their own web server. They want access to the data sets, so we do that for them. Yeah. There are issues there because you give them security issues, so we might start to roll this back. There are issues giving people control of infrastructure on the network. We can tenant it off, but there's still issues. We're developing a whole load of different packaged data analytics and AI services, again, mainly in a virtualized environment. We have a whole load of storage services. We just bought a load of new NVIDIA L40 servers. So NVIDIA's fastest data center graphics card is called the L40. We've got 10 servers. Each server's got 4 of those. So this is, I think, one of the fastest visualization clusters in the UK. That's just been deployed now. That was funded by UKAA. So we're going to be, and we can put all the NVIDIA Omniverse software on there. We have a collaboration with NVIDIA to exploit that. So you can either cut those GPU servers up into virtual servers, and I can give you all your own slice of virtual server to spin your own little CAD things around, or we can group them all together and do some big, high-res show and tell type thing. So that's really interesting. And of course, NVIDIA are really streaking ahead with that whole software stack. Omniverse is really quite advanced. This is Rob Hackers is driving a lot of that for, virtual twins. We're looking at developing a whole load of kind of multi-cloud and more user-friendly ways to access the cluster. We have a collaboration with the guys that create Open On Demand. That's a US project. You get a web browser. From that web browser, you can access the cluster. You can do a load of things. You can get an SSH terminal. What's our biggest number of support tickets by volume? It's how do I set up a remote shell? Yeah. How many times the support desk gets that question? Yeah, so if we can instantiate that in Open On Demand, just click a thing, 30% of our support tickets disappear. Right. So you can, if you make things easier for your users, your support desk burden goes down. Yeah, so Open On Demand is a really interesting tool, and we're developing that. And we're also working, I'll talk about the rest later, actually. So how am I doing for time? I'm probably really running behind. When I run out of time, we'll just stop. Go about 10 minutes. Cool. I will hurry up. So the Zettascale lab. So this is an activity funded by Dell and Intel. We currently have around $10 million of real Dell and Intel dollar to put into this activity, and we're employing 20 engineers on 4-year contracts now. They'll roll, I should think. And the idea of the Zettascale lab really is to explore the use of new technologies, kind of expanding current limits in terms of scalability, user accessibility, and system management. And it's not as the name would suggest, really, in terms of trying to design a Zettascale computer, because that's a madness. Personally, I don't even believe in exascale. I think it's a fallacy. It's just a HPC center director's ego. There is no point to it, in my opinion. Yeah, others may disagree, and actually probably do. But in my opinion, exascale is a huge waste of money. Unless any of you have got exascale codes that you're keeping hidden that I haven't seen. So your SYCL guy is going to get really busy with your MPI parallelism to be able to make use of how many cores in an exascale machine? Million. Yeah. So when you come back to me and say you've got a SYCL code scaling to millions of cores, I might retract my statement. But currently, I think exascale is just hubris. National hubris, center director hubris, and we should not allow it. That's that thing. I've said my piece. So why do we do it? We do it actually to democratize HPC, because if we can use these technologies that are designed for scale, we can make them available for much smaller installations, which makes medium-sized HPC much more consumable. And that's why we do it. It's all about democratizing HPC, AI, HPDA technologies for everyone at every scale. And that's why we do this. So what do we do? I've already talked to this slide, right? I skipped ahead. This is a kind of virtuous co-design cycle, supply chain, providers, users. This is really important, that line. Forget the rest, it's just pad. Science-led technology development. Because people like me, if I'm not careful, I just do things that interest me. I think we're down what the user wants, doesn't interest me. But that's not really the right way to do it. What we should be doing is doing stuff that the users find interesting. So we should be technology-led. So having the users in this circle is really important. Help keep you honest. So we're doing a whole load of things in a Zettascale lab. Obviously, energy efficiency. I'll run through these. The red ones I'll cover off until I run out of time. Energy efficiency, one API Center of Excellence, because obviously we're funded by Intel. I also happen to believe in it, which is also useful. If you believe in what your sponsor wants you to do, it kind of helps you rest all those conflicts of conscience. Middleware, research computing middleware, accessibility and tools is a big push. Storage is a perennial problem, right? Especially at scale. How do you remove the storage bottlenecks? Yeah, this is still a really big problem. HPC networking technologies, visualization, and trusted research environments for health informatics is a big push. I'll start to talk through some of these. So obviously, energy is a thing. So my power bill last year was £1 million a year. This year it's 2.5 million. You try explaining that to the university. That's an interesting discussion. And so energy is a real thing. An exaflop is 50 million a year, the current costs. So the operational costs really are driven by power. Power drives 90% of the cost of your data center. You know, the physical building, the bricks and the empty air don't cost anything. It's all power and cooling. 35% of the whole life cycle cost of an HPC system is the power. Yeah. And of course, any large scale activity now has to come under your organization's net zero thing. That's an interesting discussion when I go to the vice chancellor and tell him I want to deploy a 7 megawatt supercomputer that is orthogonal to the university's net zero plan. Yeah, funnily enough. So you need to get a grip on this. So we've been looking at, and the main, apart from efficiencies in the data center, which I've kind of already talked about, in cooling and UPSs and powertrain, so you can get efficient in the data center. We've got a lot of work looking at data center efficiencies. the other main control lever you have is frequency control of your GPU, because it would not be news to you guys that the power consumed by a processor is proportional to the frequency squared. I guess you can all add up, and so that's not a good thing, right? So if you turn that frequency down, you get really big goals. So we did this with our GPU machine that we call IWOCL. We got that to be number 3 in the Green 500 in 2021, and we did that by frequency control. And we just turned that clock speed down. This has all been written up in the paper that you can find on the Dell website somewhere. And so this is all done by Athena, one of our RSCs that work for Chris, that's now in NVIDIA. Really good work that Athena did on that. And so with this graph, this, which one is which? Where's my key? That's frequency, power. So as you turn the frequency down, this is the native clock. We turned it all the way down to here. The power consumed during an impact run is here. The time that run takes is here. So obviously, as you slow it down, the time goes up. The energy is here. If you slow it down too much, the time goes up so high, actually the job runs for much longer and the energy to solution goes up. But there is a sweet spot, and different codes have a different sweet spot. And so you need to probe those a little bit. But you can save 40% of your power consumption during a run, with an 18% increase in runtime. The sweet spot here was actually saving us 25% of energy to solution just by doing some blunt trick like that. And when you're at a megawatt, 20 megawatts, that's a big difference, right? So this is really worthwhile. Intel have a similar tool called GOPM on the x86 nodes, which does dynamic frequency scaling, which actually holds a lot of promise. And we had an intern, PhD student, looking at that last year. We're carrying on that work. We should be publishing some outcomes on that soon. But there's a lot of things to do with just frequency control. So just on our SYCL work, before I run out of time. So we have a plan to employ around 7 research software engineers using SYCL on a range of different codes, which I'll come on to. But apart from doing their development work, this is one of our RSE ladies, Stephanie. They learn about SYCL and implementations in their day job, and then they do outreach and hackathons and training. And so we use people that are embedded in SYCL. We've done a whole load of these different training days and hackathons and things like that. Is that you, Chris? Yeah. In action. So this is something we want to be doing more of these. As we employ more engineers, work on more projects, we build up a knowledge pool, and then we want to transfer that knowledge out to the wider community. So there's a whole load of codes. I'm going to go for these really fast because I haven't really got much interesting to say about them. Chris is here if you want to know about it. This is actually your code in the back there. So there's the general relativity code that's been ported via many different activities. Phoenix is from Garth Wells. It's finite element analysis. It's quite a key UK code that's been worked on. Arepo, the N-body, hydrodynamics code. We've been looking at MPR flows on that system. Some Berkeley dwarves. This was quite a small piece of work that was started by Athena before she left. I think this is probably going to be one of our main pushes. I think we'll get a critical mass of engineers working with Cullen in partnership with Simon's group. I think this will probably, instead of spreading those engineers thin on lots of different projects, I think I'm going to concentrate them mainly into a whole load of codes in Fusion. It's cross domain, so it's interesting scientifically, but I think it's a really worthwhile goal to work with those guys in Cullen. So I think we're probably going to put most of our focus on a range of codes around diffusion work. And CASTEP is the other one. This one will probably still get a lot of focus, actually, because we have a history with CASTEP here. Don't know if Arian's here in the room. There, you can ask him. Don't ask me, I'll ask him at break. That's actually looking really quite interesting, because this is a key electronic structure code. CASTEP is a key UK code that's been around for a long time. It's been really modernized completely by Phil Hasnip up in York. And Arian's doing a kind of part-time PhD with Phil. And this is looking really quite interesting. And performance is okay, medium? Get in there. It's getting there. I'm probably out of time. How long have we got, Simon? Yeah, almost out of time. I'll just finish on this deck. So this is about our OpenStack work. So obviously, traditionally, you have different software silos for HPC, big data, AI, and they're different instantiations of a software layer. What we're moving to now is creating a kind of a shared infrastructure layer with OpenStack APIs, and then via Ansible, we have software-defined research platforms that sit on top of that shared infrastructure. Yeah, and so all the know-how goes into creating these Ansible roles to create these different platforms that can then be instantiated dynamically. They can be owned by a research group, and you can engage with local group IT support guys and make them a stack, a bespoke stack with Lego bricks. Yeah. And so obviously there's a full stack view on this. You can kind of also exit to external clouds from this software platform. It supports the whole DevOps tool chain, which completely changes the way HPC teams work. They can work in a more DevOps orientated way, which is obviously better. I don't need to talk to you guys about that. But it's really this idea of dynamic science platforms on top of the shared infrastructure. We've been doing this for 6 or 7 years. We have a strong collaboration with a UK SME called Stack HPC. This has been funded by UKRI now for 6 or 7 years. We are making this an official kind of UKRI sponsored middleware program. So as a UK university, you'll be able to go to the Git repository and pull this down. You can contribute. We're going to be supporting it. We just got a major new funding initiative coming through from the SKA. So we've now got another 3 years funding to employ another 6 engineers creating this stack. And there's real heavy momentum behind this. I think it's a really interesting way to provide services. And I think I have used my time. Thank you very much, Paul.
Thank you. So, sorry, I meant to explain at the beginning, we were going to have there was another talk due after Paul's, Kevin from ARM, but unfortunately he's not able to be here. So we asked Paul if he would give us a slightly longer talk, and he stepped in. So thank you for helping us out. Yeah. Very good. We've got time for probably 1 or 2 quick questions, if anyone has one over. Alexander's going to come around to you with the mic.
Have you done any analysis on switching to ARM CPUs for your energy and performance issues?
Currently, no. This is Simon's forte. So we have a kind of a strategic relationship with Intel. There hasn't been enough of a driver currently for me to change. So on the x86 work, no. Obviously, the GPU work gets us our real energy efficiency. So we try to push codes onto the GPU to get real energy efficiency. And to try to edge that up, we're now looking at this frequency control on x86. But we have not had much of a focus on the ARM ecosystem to date.
But this is something
for many other reasons.
We'll probably partner on this a bit more.
Yeah.
So one of Paul's systems that he was talking about is CSD3. These are tier 2 national systems in the UK. Yeah. And I run one called Isambard, and our focus has always been on building that on ARM processors, and we're about to do Isambard 3 at the end of this year, based on the new NVIDIA Grace ARM CPUs that are coming out.
Because more than the energy, I think it's that whole kind of software ecosystem around ARM, which is the focus, and Simon's had a real push on that. So there's no point in us we divide and conquer. And so Simon's been developing the ARM ecosystem, and when that's ready for me to consume, which I guess it virtually is now,
Pretty much.
but
is,
it's taken quite a lot of effort to get there over the years. It hasn't been so generally consumable, but I think the ARM ecosystem is really coming up. So if you were to ask me that question probably in 18 months, I would be able to give you an answer.
There's a question at the front as well.
So have you considered using like a intelligent power allocator to target, say, temperatures and scale the frequency accordingly to target a temperature which would allow you to reduce costs?
Temperature is not really the thing. As I said, temperature, my cooling is only 7%. So we need to keep temperatures in operational limits, but the temperature itself is not a driver of cost. So we actually run the data center hot. So how we deal with temperature is we let it get hot. We have very high ceilings, hot air goes up, cold air comes down. And so we run the data center as hot as we can within ASHRAE. So temperature is not really a thing. That metric does not correlate to cost. So we don't do it now.
Thank you. Now you're going to be around for some of today?
Yeah, I am around.
So I think in the interest of time, I'll have to move on. But if
Yeah.
Paul's going to stay here, you can catch him later on in the breaks and ask him any questions. So let's thank Paul again. Thank you very much, Paul.
Hey, you're welcome, Simon.